Thanks, everyone. We appreciate being on the program. This is a bit of a continuation from our paper that we presented last year. This is joint work with Antoine Didisheim, who's at Melbourne, a student of mine at Yale, Barry Kuh, and my frequent co-author on this agenda, Senyon Malamud. So we're going to be talking about complex models, that is, models that have very large numbers of parameters in them. Okay, so we're going to be particularly kind of going after the machine learning perspective of asset pricing. I started with this slide last year. I want to do it again. Okay, so most people that were trained in kind of our generation were trained on this idea of the principle of parsimony. So I have this quote up here from famous time series textbook. It's important that we use small representations for models. But this principle clashes with modern machine learning, right? So we have very successful models that exist that fly in the face of the principle of parsimony. So, of course, can't go too far without talking about GPT these days, about 1 trillion parameters. I've been working on models with, compared to GPT, are much smaller, but are still very large from an asset pricing standpoint. And I think what's interesting is that from the perspective of, this lineage of Box-Jenkins, these look like crazy models. They're enormous, profligate, probably going to overfit. And then based on this idea of the principle of parsimony, it's really about we like parsimonious models because we think they're likely to be the best models out of sample. Right? But we don't have to look in finance. We have lots of evidence outside of finance already that suggests that very rich models are the best models out of sample. Small models do much, much worse out of sample. Okay? So the difference between in-sample and out-of-sample is going to be very critical for what we talk about today. There's a great paper that does a comparison in machine learning problems like image recognition and text forecasting that shows that bigger models unambiguously do better out of sample. In fact, these models are so big now that they have so many parameters, they can always exactly fit the training data. You can have 2 models that exactly fit the training data, and the larger model does better out of sample. Right? So we're going to talk more about that as we go. So I would say that from an out-of-sample performance standpoint, modern machine learning has turned this principle of parsimony on its head. Now, I'm sure that my discussant and a lot of the discussion around this paper more broadly relate to things like small models can be good for some things. The principle of parsimony can be useful for some things. Things like simple descriptions that we can understand in intuitive ways, right? But it's not good for optimizing out-of-sample performance. Okay, so that's kind of a high-level take on large models. Let's talk about what we're trying to get at here. So I think about this as sort of starting from this perspective that we've had a lot of recent advances. Actually, a lot of them have been presented at this conference over the years about using machine learning methods for asset pricing problems. Right, these methods work well. They've demonstrated large empirical gains over simple models in terms of their out-of-sample performance. All right. But there's a lot of sort of skepticism. I think it's a healthy skepticism about these results. A lot of it is rooted in this idea that we don't have a very clear theoretical understanding of why these results emerge. So this agenda is really designed to kind of build that case from a theoretical perspective. Right? As I've said when I've presented this paper before, this is a statistical theoretical perspective. Right? There are going to be discussions about things like economic mechanisms and so forth. Those are interesting discussions, but they're not really appropriately placed in the context of this paper. So the first work in this agenda was the paper that I presented last year. So this was a very simple environment. It was a pure time series prediction environment. All right? Here, we established this result that if I build very large, complex prediction models, they unambiguously do better out of sample than smaller prediction models. Okay? That was a simple environment. These simple environments are clear for sort of laying out the intuition for why this works and getting people sort of warmed up to the idea. But now we're trying to do something that's a little bit more serious from an asset pricing perspective, which is to look at complex asset pricing models. Right? So we're going to be thinking about this, for example, in the context of an SDF model. So the main theoretical result in this paper is that SDF performance is generally increasing in model complexity. So there are a couple natural ways to think about SDF performance. One is what's the Sharpe ratio of the SDF? 2 is what are the pricing errors associated with that SDF. Okay, and I'll show you that as you make models bigger and bigger and bigger, the out-of-sample Sharpe ratio of that SDF, the out-of-sample pricing errors of that SDF improve. So I take this as a theoretical justification that goes along very nicely with the prior empirical evidence that these gains from machine learning methods in asset pricing are actually in line. We should sort of expect these. And I'll spend some time on direct empirical support for this theory. Okay, so let me start with what I'll call a brief history of complexity in the cross-section. Right. So we can always think about SDF representations in terms of managed portfolios. So this is sort of a Hansen-Richard starting point. So if I want to be thinking about conditional pricing models, right? So I'm going to have this optimal portfolio that defines the SDF as being formulated conditional on some information, and that's going to be summarized by this data in a collection of variables we'll call X. All right. Now, cross-sectional asset pricing is all about understanding that weight function. How do I decide on what the appropriate weights are on all of these individual risky assets when building my SDF? Everything that we do in finance, when we do asset pricing tests, when we calculate alphas for individual assets or portfolios, it all is mappable to this weight function W. Okay. So, of course, the fundamental challenge in our work is about estimating this W. This is a really hard problem. W is potentially a very complex function. I will argue it's sort of unambiguously a complex function. Financial markets are very complicated. They're very sophisticated systems, and we have oodles of evidence that asset prices are, I don't know what the right phrase for it, very conditional, right? Their behaviors change a lot from one state of the world to the next. All right. So how do we typically approach this in the empirical asset pricing kind of paradigm? Well, we restrict the functional form of W to sort of avoid the complexity. So a great example would be the Fama-French model. You can view the Fama-French model as a parameterization of W. We're going to make W depend on something like a constant, so you're going to have a market factor, the size of an asset, the value of an asset, so you have size and value factors. All right. There's a really nice paper by Bryan, Santa Clara, and Valkanov that sort of generalized this, formalized this point. All right. So what does this do? If I write this type of specification, I've chosen a specification. I've taken that heroic step of saying that this is the way that the world behaves. Now I only have 3 parameters to estimate. Right? That's a very tractable estimation problem. All right, there are other interesting approaches to making this problem tractable and low-dimensional, i.e. simple as opposed to complex. For example, Kozak, Nagel, and Santosh have a nice way of imposing some simplicity by using principal components of factors. Right? It's just a way to control parameterization of a model. And there's some interesting role for theory for thinking about how I can constrain parameterization. All right. In this paper, we're going to take a different tack. The tack that we're going to take is that I want to model this W function not by restricting the parameterization, but by expanding it. All right. So I want to saturate my W function with conditioning information. So one way I could do this, for example, is with a neural network, but there are lots of ways to do it. What I want to do, though, is emphasize that the philosophy behind this is that we don't know what the right model is. It makes sense to specify a model if you know what that model is. But if you don't know what the true model is and you make a specification choice, you're misspecifying. And that's why small models tend to do poorly when you go out of sample. All right, so I want to try and see what happens when we go the other way and allow for big, rich, flexible models. Can they perform well out of sample? All right, so an example for an approach to how you could go after this, you could use, for example, a neural network. The nice thing about neural networks is that they give you a general approximator. It says, this is just non-parametric statistics, right? It says that I don't need to know what that function is. As long as I use enough parameters, I know I can get an arbitrarily close approximation to it. It means that I can start to eliminate specification bias. Now, I have to deal with the other side of that, which is now I have a lot of parameters. But that's what this paper is about. All right, so how would I use, for example, a neural network? I'd start with my conditioning set, the X's. I'm just going to blow it out to a much bigger conditioning set. That conditioning set is going to be a bunch of nonlinear transformations of my original X data. By doing this big expansion via, say, a neural network, and there are lots of other ways you could approach this, what you're doing is you're trying to say, how much can I get out of my data? I'm going to look at all of the forms of nonlinear associations, linear associations, everything that I could possibly get out of this data. That's what I'm getting from this expansion here. I'm giving myself the opportunity to approximate that W function more and more accurately by making the expansion bigger and bigger. It's just a basis expansion. All right, now one thing that's kind of cool about this is that this neural network can just be sort of formulated as a linear model of nonlinear variables, right? So my SDF now was something about W of x times r. Well, via this approximation, I end up looking at something that looks like a factor model. We're back to a factor model, right? The only difference here is that it's not a small factor model. If I want to have a good approximating model, I need a big basis expansion. I need, in principle, an infinite number of terms. That's fine. I can use a very large number of factors in my SDF. That's what we're going to do. And then we're going to ask, does that SDF do well when we go out of sample? OK, so quick summary of the layout of the problem that we're working on here. There's some true SDF out there. We don't know it. So what do? We use an approximating model. The approximating model has p parameters, one for each of these sort of nonlinear characteristic factors, if you will. The objective, and this objective is important, I think it's probably going to be a point of contention in the discussion, is that the objective here is that we're looking at how do you maximize the out-of-sample performance of that SDF, right? I'm not asking how do I figure out what the true economic mechanisms in the world are. I just want a model that works when I bring it out of sample. All right, so with that objective, I have a choice. The choice is not easy because I have a constraint on me. My constraint is that I don't have infinite data. I have a fixed number of data points, t. So now I have to decide on how complex my model is. How many of these nonlinear factors should I use? How many parameters should I put into my model? All right. Well, there's a trade-off. If I use a simple model, right, I have a low variance estimator, parameter estimates converge, I go out of sample, I have low variance of my SDF. That can be attractive. But if I use a complex model, I have a better approximating model. But it may not behave very well because I have so many parameters in there. So that's the trade-off. We can summarize this then with a really simple question. How big of a p should I use in my approximating model? How many factors should I put in my SDF model? All right. Well, if you're looking to maximize out-of-sample performance of your SDF, the answer is unambiguous. You should push p as large as you can push it. So now we're talking about things like the bounds of computability, right? If you have no computing constraints, you should use an infinite number of factors. In reality, we do, so we should just use very large factor models. All right. So in terms of the environment, this is the environment that we have in mind. Fairly standard. We have n assets, right? Those are risky excess returns. The empirical SDF that we're going to be looking at is formulated like this. All right. Now I'm going to be thinking about these S's as generated features. I don't want to be thinking about expanding the size of my model by adding a bunch of new variables that are sort of not important variables because I've already exhausted the important ones. Think about it as I'm adding new variables by looking at richer and richer nonlinear transformations of the original data. Okay, just using the data in a more flexible way. This is the idea of a neural network, and we'll come back to that a little bit when we get into the empirics. All right, so in the end, what I have to do is I have to come up with an estimator for this model. In particular, I have to figure out how to estimate these SDF weights. Okay, well, this is a standard problem. I could represent it as a max Sharpe ratio problem. Okay, this goes back to this Britton-Jones paper in 1999. It says you can estimate SDFs by just solving a tangency portfolio problem. Now, because we're going to be looking at very large environments, we're going to need penalty terms here, because I might not have enough data points to solve this problem otherwise. I might have more parameters than I have data points. Shrinkage becomes essential. All right? So we're going to be looking at a ridge type of shrinkage. An absolutely equivalent formulation would be as a pricing error minimization problem. So minimize the sum of squared pricing errors for the assets in the economy. Again, it's going to have to be a ridge penalized version of that problem. But the cool thing that pops out from that solution, right, you set up that problem, the solution is straightforward. It's a ridge-based mean variance efficient portfolio. I have the mean of my big set of factors. I have the covariance of those big factors. But because that covariance matrix might not be estimable because I don't have enough data points, I have a ridge penalty term in there to regularize. All right. So what I'm going to do is I'm going to work off of this environment, and I'm going to show you some theoretical results. I'm just going to show you pictures that describe the theoretical results for how this estimator behaves when we go out of sample. Now, what I'm particularly interested in is characterizing out-of-sample behaviors. They're theoretical, expected out-of-sample behaviors. That's what the work is in the paper, characterizing the SDF in that way. And in particular, I want to focus on this contrast between simple models with small p and complex models with very large numbers of parameters. Because we need to think about this as an environment where the number of parameters, p, is getting very large, but the data, t, is fixed, I need different limit theory than we have in traditional econometrics, right? I need random matrix theory. I need to be able to work in environments where this matrix has a dimension that's going to infinity, but the data set size is fixed. All right, so that's kind of the machinery that's going to be underlying the results that I show you here. We're not going to get into the detail of the machinery. Instead, let's look at some of the behaviors. So here is an example of what comes out of this theory. I'm going to show you two quantities first. So the top picture is going to be showing you the variance of the SDF that I estimated. This is the expected out-of-sample variance of the SDF. The bottom picture is going to be the expected return of that SDF. All right, so let's understand what's going on in this picture. So I start on the left. I have low complexity models. That's where I have the number of parameters is very small relative to the number of observations in my data set. Simple, parsimonious models. And as I move to the right, I have more and more parameters in my model, richer and richer approximations showing up in my model. Okay. So what happens to the variance? If you want to understand the virtue of complexity, understanding the variance is the key. Everything else is actually pretty straightforward. Okay, so why is it that the variance of my estimated SDF looks like this out of sample? Well, I start with a small model, and the SDF out of sample has small variance. This is exactly because whether I have a correctly specified model or not, if I have a lot of data relative to the number of parameters, those parameter estimates converge to something that looks like a constant. So my SDF behaves stably when I go out of sample. Now, as I start to increase the number of parameters, what happens? Well, that data gets spread more and more thinly. I get further and further from convergence of my parameter estimates for the SDF. So the SDF has more variability when I go out of sample. In fact, you can think about this as just running a regression. This is another way to estimate the SDF. We're running a regression. And when I run a regression, there's a convenient way to think about that estimator. I'm solving a system of equations. I have t equations, one for each observation, and I have p unknowns, one for each parameter. All right, so when I'm on the left side of this c equals 1, right, when the number of parameters is less than the number of observations, there's a unique solution to that system. And as I get parameterizations closer and closer to the number of observations, I get further and further from convergence of those parameters, but I still have a unique SDF solution. When I get to c equals 1, I have exactly the same number of unknowns as I have equations in my regression system. I've exactly fit the training data, right? That's a very volatile estimator. And so, of course, the variance spikes here. So if you want to understand where the virtue of complexity comes from, it comes from the surprising behavior when you take complexity above 1. You start to introduce more parameters than you have observations. All right, so why does this happen? This happens because I need to start doing some penalization to solve this problem. The reason is that when p becomes greater than t, that system of equations now has an infinite number of solutions. All of them exactly fit the training data. I, as the econometrician, need to make a choice about which of those solutions I want to use. Well, there's a very natural choice to make. Pick the low variance solution. Pick the one with, say, the smallest L2 norm. That's the ridge solution, right? So I can have very complex models that fit the training data perfectly, but they start to have lower and lower variance. Why is the variance decreasing as I keep pushing P bigger and bigger? All those models are exactly fitting the training data. The reason is, as I expand the space of solutions by making P bigger and bigger, like we're talking about orders of infinity, right? If I go from C equals 3 to C equals 4, I've expanded the space of solutions. So now I can find an even lower variance solution that exactly fits the training data. That's the surprising behavior of complex models. If you want to understand why complex models are surprisingly good out of sample, that's why. Now, the expected return result, notice that expected returns are just increasing in the number of parameters. That's actually pretty obvious, because as I add parameters, my model becomes a better and better approximator of the truth. I should be able to get a better expected return. We would have always thought that. That's just about having a less and less biased estimator. What's surprising is that we thought the variance would have kept going up as well, but it starts coming down. All right. So when you put these two together, you get the main theoretical result. The Sharpe ratio of the SDF is increasing in the number of parameters. There's this dip at C equals 1. It's not because C equals 1 is a bad model from an expected return perspective. It's a bad model from a variance perspective. But if you push P bigger and bigger, you get good models both from an expected return perspective and a variance perspective. All right. And as many people, especially on the AP side, will know, the Sharpe ratio of the SDF is a particular inverse mapping to the pricing errors that that SDF has for any set of test assets that you're going to look at. So you see price errors go the other way. So when I'm at C equals 1, pricing errors can explode, but the best models in terms of pricing error are always going to be the very large factor models. Again, this is in terms of out-of-sample performance. All right. Now, I need to be careful with my time here. I want to talk briefly about the empirical analysis. So I'm going to analyze a very standard empirical setting. All right, we're going to be looking at monthly returns on US stocks from CRISP, 1963 to 2021. The raw conditioning info X is going to come from the same data that Jens was looking at a moment ago from this replication crisis paper. And I'm going to build a bunch of models. And I'm going to look at models that are small, models that are large. I'm going to look at their out-of-sample behavior in terms of SDF Sharpe ratio and pricing errors. Okay, so let's take a look at what we have here. Now, there's one trick to getting my empirical analysis to line up with the theory. In my theory, I have this nice notion of a comparative static. When I go from a simple model to a large model, what happens to its out-of-sample performance? It's a difficult thing to do in the data, but it turns out that neural networks are beautiful for this. Because what I can do is hold the information set fixed and just vary the number of sort of intermediate transformations of that data that I use to govern the richness of the model that I'm going to look at empirically. So my input for every model that I look at is going to be identical, 130 characteristics. This is not about adding first momentum, then value, then size. This is about adding all 130 characteristics at once and then just varying how richly I use them. So a P equals 1 model, a model with one parameter, is going to be one nonlinear transformation of these raw inputs. One basis term in my expansion. A very rich model is going to be thousands and thousands of basis terms in this expansion. All right? I've held the information fixed. I've distributed that information in an ex-ante democratic way across all of these transformations. So from an empirical standpoint, all of these factors, they're sort of on equal footing. All right. So what I can do now is I can look at what does the out-of-sample performance of these empirical models look like. So empirical models are indexed first in terms of their complexity, their number of parameters. I have T fixed here, so I'm just varying the number of parameters in my model. And I have a couple of different lines. Those are when you pick different ridge shrinkage parameters. But the point is clear. The pattern in terms of out-of-sample performance in the data looks exactly what the theory predicted. All right, so as I increase richness of my models, Sharpe ratios of my SDF are increasing out of sample, pricing errors are decreasing out of sample. Okay. All right, now, a couple of quick kind of robustness notes. This is not about some sort of special behavior of small or micro or nano stocks. This is not about transaction costs or frictions. If I look at just the largest 20% of stocks on the NYSE, these are mega stocks, right? You see the exact same patterns if I do the estimation just in that environment. Of course, the levels of those Sharpe ratios are shifted down. These are more efficient assets, right? But you still see the increasing pattern with complexity. The point is large models versus small models. That's the virtue of complexity comparison that we want to be making. Next, it's not about the set of inputs. Any set of inputs that you use, any set of x's that you use, you can use better with big nonlinear expansions of those x's. So a great example would be the Fama-French model. So let's say that I restrict my input data to just the 5, kind of 6 Fama-French characteristics: size, value, profitability, investment, and I've added momentum in there. And now, so those are the inputs to my neural network. I can still make my neural network either very small or very large. See the exact same pattern. As I increase the flexibility with which I use those 5 characteristics, more and more nonlinear functions, the SDF Sharpe ratio is increasing, pricing errors are decreasing. And then lastly, I brought up this Kozak and Nagel paper. They have this interesting point that if you use a bunch of anomaly characteristics, take principal components of those principal components serve as a pretty good small factor model. What we show here is that principal components of these factors are too reductive. They don't capture the same information that you get from the full collection of factors. So what I'm doing here is I'm saying, what if I increase the parameterization of my SDF model, expand out the number of factors to, say, thousands, but always take the 5 top PCs, regardless of whatever model size that I use. You see a virtue of complexity here, right? If I just keep 5 PCs and increase the number of raw factors, 5 PCs of more factors is better than 5 PCs of fewer factors. But also, it shows you that that 5 PC constraint is too much of a reduction. You lose a lot of performance relative to using the full set of factors. That's the dotted line on top. What if you use more PCs? You see the same pattern. All right, so in the last couple minutes that I have, I think this is a difficult thing to get your arms around at first, the idea of complexity. It challenges a lot of the things that we were trained to think about. So I'm going to try and present this in a different way, just to give us a little bit more of an intuition for why complexity behaves the way it does. Why do large models do so well out of sample? All right, so just a simple thought experiment. Suppose you have a true data generating process. You know God's model. It has 100 variables that determine your outcome. Okay? So my x's are 100-dimensional in the true model. But suppose you only have 20 observations. What should you do? Should you use a deliberately oversimplified model? For example, just pick the 3 most plausible x's based on some criterion, maybe an economic criterion. If you do, that's great. You'll be able to do things like in-sample tests. But this isn't very helpful because you've picked probably a really bad model. You're doing testing. That's kind of cool. But you're testing the wrong stuff. All right? No. In fact, what you should do is use all 100 predictors. You only have 20 data points, but you should use all 100 predictors. Well, this gets uncomfortable because if I use all 100 predictors, my in-sample R-squared is going to be 100%. And I'm going to have to use a little bit of shrinkage anyway. Okay. So the key point is that this is not an overfit model. You've exactly fit the training data, but you're still underfit. You just don't have enough data to learn from. The true model has 100 predictors in it. You need all of those 100 predictors to build the best out-of-sample model. So if you do this, if you use all 100 predictors and inject a little bit of shrinkage to keep things regular, that model out of sample will do better than any small model you would have reduced to. Okay? This is what is happening in complex systems. All right, so when I think about it, I think about this is just a very generic setup. Anytime you have model misspecification, that is, I think about model misspecification as you just don't know the true model. I think about that as reality. And then you want to approach that model misspecification issue with the tools of nonparametrics. Well, that means that the true DGP from this model misspecification and non-parametric standpoint has infinite parameters. But we live in reality. We have finite data. So it's a lot like this example here. You need to use complex models to optimize out-of-sample behavior. So here's a little quick visualization of what I said on the previous slide. You have a true SDF. If you knew that true SDF, this is the performance you could get out of sample. Say that that measures the out-of-sample Sharpe ratio from knowing the true model, knowing God's model. What happens if you get reductive? You say, I'm going to specify a small model. Small models are nice because they make the in-sample fit and the out-of-sample fit the same. That's what our limit theory gets us. That's why we like using small models, because traditional econometric limit theory tells us that the in-sample behavior is then our best descriptor of what the expected out-of-sample behavior is. But we pay a cost for that. The cost is we've written down a model that's too simple, and we're going to understate what we could find in terms of the behavior of the SDF. We're going to be too far away from approximating that true SDF. Okay, it's like dogmatic shrinkage before you ever look at the data. Now, what is the complexity approach going to say? It's going to say use a big model. You're going to blow through that in-sample data. It's going to look like you've badly overfit the data. But when you go out of sample, that so-called overfit is helping you. It's helping you get closer to the true model, so then the out-of-sample performance is superior. All right? It's like judicious shrinkage in light of the data. All right. I'll wrap up with that. The previous comment has some implications for how we need to evaluate asset pricing models in the age of machine learning. Things like in-sample alpha tests, or any in-sample test for that matter, is going to be out the window. We're going to need to do things like compare models based on out-of-sample performance. That's true even if you want to compare against the theory model. So I'll just wrap up. This paper is about a new theoretical derivation that helps us understand the behavior of machine learning-based asset pricing models. There's a virtue of complexity in that out-of-sample performance of AP models is optimized by pushing model parameterization large. I have a couple of caveats here. Be happy to talk about later. But thank you all very much for your time.